Happy New Year.
Yeah, Happy New Year, Luca.
Nice. Yeah, Thomas. So how's the break been for you?
Awesome. Lots of reading. Maybe if I want to recommend one thing, it's Samantha Highway Orbital. Uh, well worth the praise that it received.
Nice. No, I haven't read it. Uh, but I also took a big break. It's been, a nice couple weeks, lots of family, lots of, I I did some Japanese Duolingo just for the fun of it with my kid. So that was good. It
Yeah,
was a lot of fun. And then what else? Yeah, I read a bunch of papers and had a lot of
in the
wacky
Christmas
ideas of
break.
things.
In
Sorry?
the Christmas break, you read the papers.
Yeah, yeah, because I don't have so much time to do that, right? And I have my wacky ideas on how things work under the hood, blah blah blah. So I wanted to see if they were wacky or not, but I will never be able to follow through. So whatever. Now, I will wait for
Yeah.
Meta to publish their papers.
So, so what was the thing that impressed you most from the
Ah,
papers?
well, yeah, I had a long detour on uh, on several things, but one thing that I reread, actually, I reread yesterday because I was on a plane, and so I took the Almo 2 and the DeepSeek V3 reports, and gave them a good reread because I kind of skimmed them, in the daily. In busy times usually. So I had the time on the plane. It was a Ryanair flight, so no in-flight entertainment.
Right.
You're crammed and so on. And so I was reading through those reports, and I think I have them here, so I can definitely recommend it, both of them to whoever is watching us. Okay, so this is our usual other
Yeah.
session thing, but here I have my books thing, and the Olmo paper is great. So Olmo is this model here, this Olmo 2 report. So Olmo is this model from Allen AI, and it's not the best open source model out there in terms of performance, but it has the unique feature that it's all completely open source from top to bottom. So they shared everything, the methodology, all the data sets. And when you say data sets, it's also the precise data mix and the checkpoints in between. And so I think, this is a way reports need to happen. And it's a way like full transparency is kind of makes sense. And if you have a scientific background, this is the bar that should be the standard bar. But given the set state of how things are shared in our field, this is up there in terms of being able to even hope to reproduce things. And so here you can see all the basic instruct and the training code, the eval, and all the data. And so I recommend everyone to go through it because it kind of explains very well what is emerging right now in terms of, we have been used to say, okay, there's pre-training and then there's fine-tuning or instruction tuning or alignment, and now it's regarded as post-training. So it's a mix of supervised fine-tuning and reinforcement learning, or what kind of like sub reinforcement learning there is nowadays. But it also focuses the attention on this thing called mid-training, which is very interesting. So you pre-train a model on the most of the tokens you have, not high quality, and then you do, and learning rate there needs to ramp up from 0 to some number, and then you have cosine decay up to a certain point, not to 0, and then that's where you start mid-training. And mid-training, you select a very high quality set of data mixes, and still next token prediction. But you do it by annealing the learning rate and only training on that mix. And and it's not a big mix because it's about 10 billion to 100 billion tokens. So it's not a lot.
And
But
usually
that's
you train like a small number of trillion tokens, right? Like 4
yeah,
trillion. Of,
yeah, 4 trillion before, but then you have this like mid-training thing where, it's very high quality, not a lot. Like once you've made your model able to learn to read and understand kind of, then you do that phase and you see the benchmarks like going up, and the quality of the model really ramping up, and that's before the post-training stuff. And so if you think about like companies and so on, they will focus a lot of, instead of like pre-training on your company data mix, you can mid-train on your company data. So it's very interesting from a dynamic point of view, and I think we'll see a lot more of that. And here, just, I don't want to get started on that, but then, whoa, that was very accurate. I wasn't expecting it. In paragraph 6.4, there's a paragraph on maximizing hardware utilization. They talk about how important the compiler is in doing that torch compile. And then a few tricks on minimizing host device syncs and what you need to watch out for. And interesting asynchronous bookkeeping with a separate backend so that you don't block on doing certain operations and so on. Yeah. Anyway, very much a recommendation. But the other paper that I read was the DeepSeek v3 technical report. So DeepSeek is a model from China, and it's pretty large. It's a mixture of experts with 670 billion parameters trained on 15 trillion tokens. So it's a massive amount of data, massive amount of parameters. Only 37 billions are activated though, because it's a mixture of experts where you have certain experts that are always there and certain experts that get selected. Anyway, very interesting. But the interesting thing about this report, which is also very detailed, although it's less open than the other one, is in the training framework part. I mean, a lot of it is very interesting. In particular, I would say that there are at least 5 papers in here. There are things that like one paragraph could be exploded in a full paper. But apart from that, because they use multi-token prediction and a lot of very fancy stuff. But the training framework section for us, like involved in whatever we are involved in, it's interesting because it shows you how many optimizations they did to pull off, training efficiently on a model of this size. They spent like 5 million for this training run, which is for a model of this size is very efficient. And they had to optimize their framework, not only from the source code perspective, but also, taking into account the topology and the hardware. And a lot of the things that they describe here, like this is a pipeline parallelism scheme that they implemented and optimized, very sophisticated. And then how they manage cross-node communications compared to intranode communications. And then what they choose to recompute, remember what we talked about last time, and what they need to share. So it looks to me that if you're doing this, you're either working at the source code level, or there's really a place for people to operate at the transform level, and not delegate decisions to a magical compiler, but you need to be very prescriptive about what you decide to do as a function of what you're running on. And this is exactly the space where Thunder, we would like Thunder to thrive, right? To enable some of these things as transforms so you can apply them to generic model and not just, that one DeepSeek v3. Yeah, so very interesting, very, suggested reading all over across the board. Yeah.
Awesome.
Nice. Anyway, I'm taking way too much time here. So I know you have some surprises for us related to recomputation that we talked about. So
well, depending on how much you remember, like what we did last time, and maybe more of a surprise or less. But yeah, so obviously we looked into checkpointing, and the first time we tried that, I basically made a fool of myself because it didn't work as we wanted. And then, of course, just before Christmas, I had something that like seemed to work. And this week, we upstreamed most of it to Thunder, which was like, it's never as smooth as you want to, but finally it worked well. And so basically we can now take the checkpointing from PyTorch and capture that in Thunder and make our own checkpointing decisions from it. And so my goal here, my personal goal, is to have Thunder not like, if it takes more memory than eager, it's some sort of bug. And so it might not be a very grave bug if it's just 3 bytes, right?
yeah, for sure.
Because we sometimes decompose things or so. But so we spend like quite a bit of thinking how to get there, and now it works. So maybe we jump right in, right?
Yeah, and I'll stop sharing my screen so you can share yours. The general message, the learning for anyone developing anything is that we had kind of a stiff thing in there at some point that was potentially cool, but it was precluding us to really reason about optimizations in detail. So the general message.
So one thing here is like don't reorder things. Like the natural checkpointing order of the instructions, that is a reasonably good order, and we like drew a lot of that in detail before the break. And so my my message is that if you reorder things and you don't explicitly consider the memory impact, then you'll ruin it.
Yeah, and of course, we're dealing with a blocky model, so
and of course,
I mean,
we started doing things with smaller models for experimentation, and then things worked well, and we kept them that way and didn't notice that.
Yep.
Yeah.
Anyway,
I wouldn't know. But yeah, so if we import Thunder, then we can we're in the studio again, right? So with Torch device CUDA, we can import our favorite model. Oh, we need libgpt, right? Did I import it yet? No.
Not yet. So we'll show it in libgpt and then maybe also show it with Hugging Face later on.
From name, and what should we take? Llama 3.2.
I think 3.2. Yeah, right? Exactly.
And so we want this in bfloat 16.
Mm-hmm.
And then we need some inputs, and I'm going to be very lame here and just take one of some shape.
Yep.
Oh,
I wonder what token that is.
Whatever token it is, we just inspect the memory. So I take a batch size of 1 and let's say 1,000, 8K tokens, sequence length. and the D type needs to be int 64, right? Which is the default PyTorch int type, for better or worse. And so we have those, and if we look at the model, what happened? Name lit. Oh, and
yes.
Okay, so we have this model, and so we need to do the checkpointing. So for I in range len m transformer h.
Yep.
And m transformer h. We just wrap the ith model in this little checkpointing model that I defined before the break, and which I don't go through again. So I did a bit of weird magic here. Maybe we'll profit from it, and maybe we can skip it. We don't need it here. But yeah, so this is the checkpointing, and then we could measure the memory impact. So get max memory for model and inputs. And so what we'll do is we will first reset the stats. So memory, reset peak memory stats. And so before is torch CUDA max memory allocated.
Yeah.
And then we run the model. So just pass the inputs, and then we do res sum backward. It does not include a loss, so we'll just sum and backward. And then we get the memory after, right? So the max memory after. And now I need to get the sign right. After is larger than before because it's a maximum over time. And so
a question one might have here is, do you need to synchronize, or does the CUDA max memory allocated synchronize for you?
I think we don't need to, but no, it doesn't need to because the allocations are on the host anyways. So
yeah, you're right.
We should be good. So we can do get max memory. Should we do it for the full model, or should we take like a smaller one to?
Yeah, we can take a smaller one, so it's easier also to compile later.
Lit GPT, no, config, right? From name, and when I do config, I can take the name and I can modify the configuration with these arguments here. So num layers, layer or layers? I can never remember.
I don't know. I can verify it for you.
Oh, we can just like risk it, right?
Yeah.
So, yeah, it's num layer probably. No, n layer. There's a fourth option in layers, but it's n layer. At least it does the right thing and doesn't silently like say, "Oh, it's all okay," and then it doesn't work. Which is a good feature, right? Everybody likes breakage more than silent breakage. Well, I don't know. Okay, so I need to get my maths right for the gigabytes. So this takes 4.7 gigabytes to run through 4 layers. And I can now run Thunder through it. So Thunder JIT. And then, oh, and I wanted to try whether it's stable. It's stable, which is good. Sometimes because the first run will allocate gradients, so that will be a bit larger,
Okay. Yeah.
potentially. But so then we can compile the model and get max memory of the Thunder module and do the same division here. And yeah, so this basically would work the same on this Thunder main branch. I'm with the bit that we showed last time that didn't get upstreamed is the estimation of the memory. I have an open draft PR for that, but it's not quite working yet. But so this takes a while compiling things, but then now we see that it's like super small. Why was that?
Would you checkpoint? Yeah, can we verify we checkpointed the eager?
So this is checkpointed, but we also checkpointed the eager.
Interestingly, we did.
And it's not like M. I don't know what's a parameter. M transformer embedding.
I think is it embedding within the transformer?
WT.
Yes, WT. Yeah.
Okay, so does this have a gradient yet? Yes, it does.
Yeah.
So so there's not much reason why this would be that much larger. Do we believe it? Do we not believe it?
Well, before the call, before coming online,
so,
kind of saw something similar, right?
So before the call, we saw like the same thing for now it's
phase, right?
now
it's
now it's the normal. Maybe something went wrong somewhere.
Or maybe you need to synchronize.
Yeah, so
it could be, right? Because if it's still doing its intermediates thing and you take
I mean, before you call the kernel, you have all the allocations, I think. But now I reran the Thunder module. But yeah, so maybe this gets it right. The trouble is that if we get the right answer here, we never know whether that's because we fixed it or
absolutely
because this. But
yeah,
yes, this is kind of what would be the expected result from my point of view, and so this is what it does. And of course, you can inspect the checkpointing. One thing I've not done very well yet, it needs improvement, like all software needs improvement, is that when you do Thunder last backward traces, JM and 0 would be the first, but so here it doesn't save the original trace, but it immediately saves the backward rematerialization trace. We need to fix that. But so you have this here, and interestingly, if you do, and we can do this Thunder. Oh, but yeah, we need to. If we delete the last used, so this doesn't have yet that we delete everything. So if we do that, del tr is Thunder core.
So now you're gonna apply a transfer manually on the
Right.
trace, right?
Thunder, and I need to remember where it was, but I think it's here. Right.
Yeah. We should probably move it. Yeah.
Yeah, we should fix all the things. But so now we can do import from Thunder examine memory calculation. We can get the get alloc memory, and we can have mem and some parameter that's not interesting to us, and this is get alloc memory from the deltr, and then I can print the memory. And you see that this is, I mean, I didn't do the dividing yet, but this is 10 gigabytes, which is too much. And the reason is that we have some additional things that we save. And but if you look at the last trace, that should be a bit better. So there's more things going on in between, and I forgot to remove a print somewhere. But so actually it removes, we still see that there's a overestimation of how much memory we use relative to this, and that is because the gradients probably already exist here and we count them again. But yeah, so so there's still some bits to work out here, or maybe there's still a bug. So this is still in verification, but with this little trick, we can inspect the memory. But yeah, and so the nice thing is that this also works for Hugging Face transformers, for example. So that's one of our goals this year, right? That it should not just work for our model, but it should also work for your model out there. And so let's grab the Hugging Face llama, and I'll just grab it from here because I can never remember like what the exact commands are. And we had 4 layers, and we want training this time. And there is I think I need
that's a gradient.
Use caching
off, right? Yeah, false.
No.
Or caching, yeah. No.
Use cache. It should. Well, what? Oh, that's probably because it doesn't have the right thing yet. But so we do this and we call it like M2, and then we need to do the same trick for the checkpointing, and because Hugging Face transformers, they code the model a little bit different. And what they do is they pass parameters as keyword arguments, which you can usually do with ease, but that's actually incompatible. Or it's not called transformer, but it's called model layers instead. I think. Okay, so this like works with this little trick, which I just took from the signature of the layer forward call. And now we need to do another small adjustment, and that is if the result is a dictionary, And it's not actually a plain dictionary, but it's some subclass thing. So I can just say res is res.logit, which will be the thing we need to backward. And now we can do get max memory. Did I run this? Yeah. Get max memory of M2 and our input, and normalize it to gigabytes. And it's roughly the same, right? It's a bit less. We have something to investigate there.
Not so much, but yes, worth investigating.
Thunder JIT, so it's JM2 then, I guess. M2.
Maybe it's the positional stuff. Maybe it's the rope. And when it gets allocated, I don't know. We'll see.
Yeah, I mean, we could do it. We could also wait until we get the better estimation, and then we can look in a more detailed way.
Yeah, that's true. Yeah, we could actually compare the traces. Yeah, it would be fairly interesting to do so. Yeah. Anyway.
And so
I have big ideas for a better traces inspection thing.
Yeah, I mean, so here we have two things. One thing is to have the memory things here, and I think this should not be probably there's something that gets counted twice. But then we also we should also be able to see as the first thing the backward as it's constructed. And we see here that Thunder had a little bit less memory than the Eager, and in fact it's very comparable here, up to single megabytes to the GPT version.
So this is interesting, right? So we put the computation in our canonical form, we apply checkpointing, and irrespective of the actual implementation, we get two memory usages that are very close.
Yeah.
So maybe, it may not be that way for all the things, but I think it's quite interesting.
So one of the things that we didn't have before Christmas that we have now is at least working in conjunction with checkpointing, is that we have a path that specifically targets things that are computed inside fusions. And so inside the fusions, we talked a lot about that like reading memory and saving it back is very expensive compared to just computing a few flops. And so what will we do in this rematerialization path for forward and backward is that we check, is there something inside a fusion that's only needed for saving for the backward, and then we might as well compute it in the backward. And that's a very, very nifty part. And that enables us to get things down a bit more, like the difference here between the first and the second, that is actually from this rematerialization step.
Yeah, I think it's fascinating also again, going back to what we were saying before when looking at the DeepSeek paper, is the ability to control these things in a very granular way, I think. And we hope in the next couple of months that, even we'll be able to further simplify the semantics of how to write transforms with a bit less gotchas, because right now you can modify something you shouldn't be modifying and so on, but we'll be focusing on some of that stuff, because there's so much value, as we have seen from the DeepSeek paper, in opening these optimizations up to AI engineers, AI developers in general, and not keep them bottled up in some paths in some compiler. That's our goal.
And one of the things here is that how the checkpointing works is that while we record the traces, the checkpointing that has a look aside. If you have been watching all of the episodes and remember from the summer, the look asides that divert things. And so we divert the checkpointing. And what it does is during the running of what is being checkpointed, we don't want to save the gradients. And so we tag all the proxies that we create with don't recompute in backward. And then only the outputs and the inputs of that function are actually saved for backwards. And then after creating the backward pass, there is a pass that will like drop the things that have been marked as to be recomputed. And so if you wanted to, you could write a transform that instead does some magic, tags those, and then it will automatically like transform the backward in that way.
Yeah,
which is like pretty nifty. Maybe one can one day like look at it and decide how aggressive you want to checkpoint based on how much memory you have.
Yeah, exactly. So the checkpointing itself, it's also something you can control in the backward. So the point is also the ability to iterate through your backward and make decisions just in your plain backward, and that's also something that it's a lot of flexibility. And so maybe in some future in 2025 we'll be able to write several of the DeepSeek optimizations as transforms and take it to the next level, and I'm very much looking forward to it. One thing is that we will be probably at GTC. Well, without the probably, we'll be at GTC, and we'll have something running for Thunder. So we have some work to do to straighten everything up and get ready. So we have kind of a couple months to get everything in order. But it will be a main thing. So we'll be happy to witness this work in our Thunder sessions. And as part of that,
modular bugs, I have to say, I'm rather happy that the checkpointing now works out and the memory consumption is under control, right?
Exactly. Yeah. And all with with an inspectable effect on the traces, and so it's really ideal. Amazing. So I think this kind of brings closure to a lot of things that have been happening in the last few episodes. And so I don't know about the next thing that we'll be tackling, but I know that we'll be very close in the next episode,
Right.
So, we'll spend a week together. And so that would be great. And we'll write a lot of
all right,
that will be facing on the
next
outside.
week. This time I'll be in Bergamo, right?
Exactly, that's what I'm thinking.
Yeah.
So
I'm always thinking in like 2 weeks rhythms, but it's next week. Actually,
it's next week.
Yeah.
So next episode together, and then thanks everyone for watching, and see you next time.
Yeah.
Bye, Thomas.
Bye, Luca.